All right, we have been discussing determinacy and the dark side, indeterminacy. If a structure is statically determinate, you will be able to solve for all the forces, shears, moments inside of the structure using statics alone. If it gets too many reactions on it, it becomes statically indeterminate, and you have to solve for some deflections on the beam so that you can come in and say, okay, that deflection is not supposed to be there, and you put a force to make it go away, and therefore are able to solve for the reactions on the beam, and then you can draw the shear and the moment diagrams and design the beam. We also have been discussing deflected shapes. We're going to do a little bit more of these first two, and we'll get into influence lines. Now, we talked about taking a real structure and saying that it is the same as a primary structure, one in which any additional unneeded reactions have been removed such that the structure is not true but can be solved by statics, and adding to that a complementary solution. Where we come back in, we see the points of deflections and rotations that are undesired and undesirable, and we make them go away. This structure is statically indeterminate to the Clapton. What degree? That is correct. Some of them are quite obvious, probably the easiest way to work them, and I think it's obvious that what you'd probably do is just leave it stuck in the ground, which holds up nicely, put the load on it, 5 kips, take the reaction at A off. Now you need some skill in drawing what the deflected shape looks like. And you don't have to be real smart at it, but the better you draw it, the easier the problem solution appears. There's nothing going on up here, so none of these pieces will be bent. And then this 5 kip load will start out 5 times 0, 5 times 1, 5 times 2, 5 times 3. There'll be a linear moment inside that beam. We normally draw the moment diagram on the compression side of the beam. And so the moment diagram will be linear, and it'll reach a magnitude of 5 times 6. Usually they call that M0, the bending moment diagram for all of the little pieces, A, B, C, something new happened at D, and it's the moment diagram due to the real loads on the primary structure. You would then come in, excuse me, let me see, I don't have a colored pencil, I'm not sure it would show up in your notes anyway, so, well, let me draw another structure. Let me draw a different structure to show you the deflections. Harrison, how much bending would you have right here? Harrison here today? Okay, considering the situation. How much bending would you have right in this piece right here? Down in here, I'm going to show you the whole thing all bent final. But how much bending would you have right in here? That is absolutely correct. I mean, it's a hard answer for a student to give because, you know, you think you're bound to have something, and when you don't think there's anything, the prof's picking on you or something. But no, there's nothing there. Because there's no moment there, there's no bending. So what I'm going to do is I'm going to show you the most of the bending at the bottom, because that's where the most of the moment is. And I'm going to show it to you coming straight out of the ground, because that rascal comes straight out of the ground. I'm going to show it bent horribly, and then I'm going to show it bent not so badly, and then I'm going to show it bent none at all, and then I'm going to show it not bent at all, and then there's a right angle here, and I'm going to show you a right angle here. And when you say, why didn't point B move down a little bit? Because I have exaggerated these deflections probably about 1 times 10 to the 6th. I mean, when I show you the deflected structure, this point really moves to the left 1/4 of an inch. And does this point here move down slightly? Not that I can see. You say, well, you mean the member along this arc is just as long as the member was in? Yeah. For all intents and purposes, that point doesn't move down. It does roll to the left, and it does roll, and it does move down. And there is a motion down, and there is a motion to the left, and there is a rolling on the end. There is a movement down, there is a movement to the left, and there is a rolling theta on the end. Now let me show you the original distorted structure. I know it comes straight out of the ground. I know it kind of comes like this. And now then it's kind of a guessing game. I do know that's a right angle. And because this is a roller, there is no tendency to stop it from moving. And so my guess is the roller moved over there. My guess is there is a rolling of the end of unknown and uncared about degrees. There is a motion to the left, not restricted, and I don't care. The problem is if this point guy moves down, that's undesired. That's wrong. And so this point B moved to the left, down, and rolled. Moving to the left, I could care less, and I do not have to fix it. Moving down is a problem. That deflection down is a number I will have to solve for, usually given the symbol delta at a vertical, or there'll be all kinds of namings. After a while, there'll be so many letters here you just can't live with them. And that'll be the number 1 deflection, and the number 1 this, and the number 1 that, and someplace else it's a number 2, and someplace else it's a number 3. About all you can do is put numbers on them to keep track of them. But I'm telling you that's wrong. That's bad. That has to be fixed. And let me put the load back on there to show you who caused it. Here's the moment diagram caused by the load, and these are the deflections caused by the loads. Only one of which I bring up, because only one of which is wrong and must be fixed. So I don't care how far it went to the left, I don't care how much it rolled. So I don't care how much it moved to the left, and I don't care how much it rolled. Gavin, don't do that to me. If you're going to go to sleep, stay asleep. Because I say I don't care how much it moved down, and I don't care how much it rolled. And I don't care how much it moved down, and I don't care how much it rolled. Gavin, what do I not care about? Well, but if you wake up at that time, it's all been lost. The whole joke is gone. So pick a state and go there. That's awake or asleep. All right, now then, this is the primary structure. Excuse me, I don't want to put it that close to the thing on the top. This is the primary structure showing you the moment diagrams. This is the primary structure showing you the deflections. And now we do use only the primary structure, incidentally. Once we see this, we make a primary structure, and all of the other things deal with the primary structure. Then we have, sometimes they call it a secondary structure, sometimes they call it a complementary structure. And the loading on it is that loading required to get rid of this serious problem right here? That would be a reaction at A vertical. Tell you what, let me just admit the truth. We're not going to put the whole R sub A on there. We're going to put a 1. And we're going to see what the moment diagram looks like. This is drawn on the compression side. You should really, on simple things like this, should be able to just practically sketch them. You'll have to practically. And this is 1 times 1, 1 times 2, 1 times 6, 1 times 8. This is 1 times 12. So this would be 12. And then as you cross the corner, whatever moment's on that side of a corner is the same as the moment on that side of a corner. And the load is parallel to the member. And that'll be a 12. They usually call that M due to a reaction at A. We'll get into the naming once we really start getting into solving these things. This will be the primary structure. Good morning. How you doing? And here's the primary structure deflected because of this 1. No bending, tiny bending, little bending, lot of bending, tons of bending, monster bending, unbelievable bending. And therefore I'm going to show, I guess I'll start down here where it's fixed because I know it comes straight out of the ground. That bending right there is constant. In other words, that's rho, that's rho, that's rho, that's the radius of curvature. Has a constant moment, so it has a constant radius of curvature. And then this is a 90-degree angle. It always stays 90, and then it bends up like so. The only number of interest to you will be this number right here. That will be the deflection at A. They usually give the real loads a big delta. They usually give the little loads, the unit loads, small delta. That's what we're going to be shooting for in the long run. Another primary structure that would have been acceptable for that one and give you just as good an answer would be if you left this roller here and took this unknown moment off of here. Incidentally, there were 1, 2, 3, 4 unknowns on the structure. That's why whoever I asked said it was statically indeterminate to the first degree, and we had to take one thing off. You could have removed the moment instead. So the complementary structure could have been, leave this on the roller, leave this down here, and turn it into a pin, thereby removing the ability of this thing to take a rotation. And then you would come up with, this would be your primary structure for everything else. Probably be a little harder to work with, not necessarily a whole lot harder, but for instance, here's the one for the real loads. You know what? Yeah, that'll work. Some moments about this point would cause a vertical reaction. So that thing would probably deflect. Who knows? And who knows? Something like that. It would push it over, and it would bend. This upward force would be an upward force, so this is going to bend like that. This elevation is the same as that elevation. Now, I don't suggest you go off and get a weird primary structure just to make your life more difficult. but they are all good primary structures. Any one of them that you can, as long as it's stable. Now this one's not good. Remove one reaction, so I'm going to leave this. I'm going to put a thing here which will take axial force and will take bending, but the thing I removed is the horizontal force at that point. That's not good. That one is one of the ones that won't work, because you have no place in the structure to have a horizontal resistance. Therefore, the whole thing slides down the road and it's not stable. So, no good for that choice of releasing this member. One that would work, be weirder than all of them, would be leave that down here. Leave the ability to take moment, and leave the ability to take horizontal force so that the 5 kip load can be picked up, and then remove the vertical force. That one will work. I don't know how it would deflect. I wouldn't touch it with a stick. But it is anything that you remove one reaction and it doesn't make it fall down, that's an acceptable primary structure. All right, on this one, Nelson, how many degrees indeterminate?
3.
That is correct. That's good. 1, 2, 3, 4, 5, 6. It is 6 reactions with 3 equations of statics, 3 degrees indeterminate. The most obvious primary structure would be this, where you remove these 3 forces, these 3 reactions. Then you'd put the load on there, on the primary structure, and you would find that it moves down, and it's not supposed to. You would find that it really doesn't move to the left and to the right, and it's not supposed to. And you'll also find that it rotates, which it's not supposed to. And therefore, you will not only have to go to the construction shack and pick up a hydraulic jack to push this point back up, you will also have to put a thing on there with a moment maker and put a moment on it so that when you get it back up to here, it'll come back into the wall with no slope. And then the third thing, there are no horizontal forces on them, so really don't have to worry about those 2. I don't think that one looks that much different from most of the rest of them. The most obvious primary structure would probably be this. It would bend down. It would stay, oops, it's got a force on here too. It would bend in. You would have a delta at C vertical. You would have a delta at C horizontal, and you would have a theta at C. Love. Which one of those do you need to get rid of? Love here, L-O-V-E. And if you say it's quite obvious, and I don't even think I ought to be asked such a question, we'll just pass it off to the person in front of you. Just tap them on the shoulder and say, I'll have my associate do this, my assistant. We're getting a lot of passing around here. Which one of these 3 things that are going to happen to this structure when you let go is unacceptable? The vertical. That's the only one, is the vertical one is unacceptable. Okay, you'll be coming back in, and you'll be trying to get rid of that. Truth is, you'll put a 1 on it and see where it moves, and then you'll adjust that 1 times R sub Z to make it go back to 0. That one's no different. It's just got the roller on the left end, the primary structure with, I would suggest that would be good. That one's not much different. Oops, thank you. Primary structure, leave it fixed, take the roller off, see how it moves. It'll move down, it'll move to the left, and it will rotate. And the only one that you care about and the one that you will have to put back, make it consistent with the truth, is the vertical displacement. Same idea. I'll leave them for you to mess with. Same idea. That's not a good picture. Somebody in there ought to have some resistance to horizontal motion. We already said that when they drew this, they really meant no resistance to horizontal motion because the web is so thin. No resistance to horizontal motion. The thing would just roll like a rocker. And if this one also has no resistance to horizontal motion, well, we got a problem here. Somebody somewhere ought to tie this thing down. I will admit that real concrete beams out on the highway, they usually just, there's such massive weight on them, they just stick them on a neoprene pad and they don't go anywhere. But one of them is going to have to be considered a pin, the other one's going to have to be considered a roller. Cantilever beam. Cantilever beam. Ooh, no, it's not a cantilever beam. Look at the difference. Cantilever beam jammed in the wall. Somebody spent a small fortune making that really happen. A lot of steel, a lot of welding, a lot of connecting, a lot of care, a lot of thought. So they're not easy to make in the real world. So the way they're normally done, they're just pinned. Therefore, I would consider that to be a simply supported beam. I would let this undesired thing happen, and I'd come back in and I'd get rid of it in a secondary solution. Cantilever beam. It's just got a little clip angle shown. We already discussed that they're not any good for moment. They're great in shear. They hold tons of load in shear. But when the beam wants to roll 1/3 of a degree, there's just no way you can stop it. The bolts won't even probably hit the side of the angle by that rotation. Make it a cantilever beam. Get rid of these 2 unknowns, or those 2 deflections. Cantilever beam with a rod attached to it. Probably what I would do is I would go ahead and just say it looks like this. Cantilever beam. Let it bend. Admit that the rod is only in tension. And realize that there's an undesired deflection on the end of that stick and make it go away by pulling up on the end of the stick in a secondary solution. All right. The easy way to do this is just to make it into a cantilever beam with a bunch of junk stuck out on the side. Cut it in the middle, 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 and it becomes this. All of which are statically determinate and stable. And you don't have to cut them in the middle. You can cut them over towards the edge if you would rather. Actually, it makes the work a little less work. So you could do this, and you could do this. And then you can do this. And what happened to that thing? And then this. And that would make the work a little easier. What you do is you'll notice that you can run around in here and you can get everywhere without having any closed loops. And therefore, I don't care what the load is. You put the load on here, I can tell you what kind of moments it causes. Here's what kind of moments it causes. On the compression side, no moment, a little moment. It's getting to be like a squared because I'm multiplying the base times the height times the moment arm. The base times the height times the moment arm. You see that x distance is coming in there twice. There's a parabola. This is on the compression side because it bends the beam down. And then it stays constant. So there's your moment diagram. A lot of times you won't even draw the moment diagram because you need equations. You go straight for the equations, although the moment diagram is helpful. In other words, once you realize that's a parabola, well then when you get a parabola out of the equation, that feels good. And you know this is constant. Anytime you have a moment of any magnitude on one side of a joint, you have an equal and opposite moment on the other side of the joint. If this one causes compression on these fibers, it causes compression on those fibers, and vice versa. Now, we'll get into that a lot more once we really start doing the work to solve for these things. But I want to warn you, you need to be able to get started on that. All right. Influence lines. You have seen many of these. You have seen many structures with a load on them. Probably, though, you have never been asked to put the load on there yourself. And where you put the load on the structure influences how much moment is caused in the structure. As an example, here's a beam. It is a simply supported beam. And I have a concentrated load, 6 kips. And the beam is 10 feet long. And I know that the load rolls from the left end to the right end, and then it's past the ditch. You can put the load anywhere you want to cause shears and moments in the beam. Some of them are pretty obvious. Where would you put that load to cause the worst shear in the beam? All right, now you are obviously a moment kind of guy because you are right, putting it in the middle. You've broken things before and you say, look, you don't take a stick like this and put your foot there when you want to break it. You always put your foot in the middle and it breaks a lot easier. The answer to the question of where should you put the load for maximum moment is indeed in the middle. To cause the biggest shear, for instance, right now with a 6 kip over here looks like about 2 feet, you're going to get, if that is 2 feet, I would sum moments about this right reaction, 6 times 8 minus this reaction times 10, and I notice the reaction is reduced from 6. But if you back it up so it's 9 feet away from here, then you got 6 times 9 minus the reaction times 10. And first thing you know, it becomes pretty obvious the place to put the load to get the maximum shear is right over on the left-hand side. That's when one of your reactions will be a maximum. And as you said, to get the maximum moment, you would put the load in the middle. And you can check it out. But there are some cases where they get really ugly, and you don't know where to put the load. And for that purpose, we generate what is known as an influence diagram, or an influence line. So I'm going to show you how to generate an influence line for the left-hand reaction. And I'm going to just always use a 1. I don't care if you give it units. A lot of times we don't even give it units because if you're getting ready to use it for a Newton meter kind of thing, well, then you don't want the kips running around loose. The influence line tells you the magnitude of whatever you're looking for, depending on where you put the load.
Is that beam simply supported?
Yes, sir. It is simply supported. There's a reaction on the left and a reaction on the right. One of them is actually a pin. One of them is actually a roller. There's a reaction at A, and there's a reaction at B. Now, first off, the load is off of the span, and the reaction at A is 0. Then, when I put the reaction just a little bit to the right of point A, I sum moments about B is equal to 0 is equal to plus a 1 kip load multiplied times his moment arm. This is a 12-foot beam that I'm generating the influence diagram for the reaction at A. Minus the reaction at A times his moment arm is 12 feet, and I find that the reaction at A is a 1. You say, well, that's obvious. You put the load right on top of the reaction. Well, I agree. I probably should have seen that. Now I'm going to move the 1 kip load down the road a bit. I'm going to move it down to the 3-foot mark. I'm hoping that these points we're picking are close enough together to allow us to draw a smooth curve and be able to pick any value off of this curve that we would like. The reaction.
12 minus x.
You can do an equation, yes. And then you have to plug x in at different points to plot the curve. As a matter of fact, the book likes the equations for the influence line. So either way is fine. I think they give you about the same amount of work. Let me get this out of the way so it doesn't look like that's the load. I'm going to move down to a new picture of the structure. Here's the reaction at A. Here is the unit load. This is 3 feet, 9 feet. This is B. I'm going to sum moments about B is equal to 0 is equal to minus the reaction at A times his moment arm is 9 plus the 1 kip load times his moment arm, he's times 12. Plus 1 times his moment arm is 9, and I solve by statics for the reaction at A. Now, if you say, well, this is ridiculous. I mean, if you got a better way, show us. I will. But when these things get really ugly, I can assure you that cut, find the answer and plot it someplace will be your only hope. The reaction at A is equal to 9/12, 0 what? 0.75. So this is 0.75 kips. And if that's true, let me go ahead and say this reaction was 0, then this reaction at B would equal to 0.25 for equilibrium, some forces vertical. Now then I'm going to take the structure and I'm going to put the unit load in the middle. I got a reaction at A, and I've got a reaction at B. Due to symmetry, I'm just going to go ahead and tell you the answer. 0.5 kips, 0.5 kips. And then if I finally put the load at the 3/4 mark, then this reaction here looks just like this, reversed, 0.75, and the reaction at B is 0.25, got to reverse them, and 0.75, and when the reaction goes right over the load, the reaction at B will be 1, and this guy will be 0. Now, the problem with these diagrams is they look a lot like shear diagrams or moment diagrams. And so people start getting the idea that what you've really got is a shear diagram or a moment diagram. And that's not the case. But it is a subtle difference. An influence line. Draw an influence line for the reaction at A. Here is an influence line for the reaction at A. An influence line gives you the magnitude of the item you're looking for when the load is located at that point, at a given point. So when the 1 kip load is here, the reaction at A is a 1. And since it's going up, and I assumed up was plus, I'm going to draw you a 1. When you move to the 3-foot mark, the reaction over here on the end went to 0.75. And I'm going to cheat here so it looks halfway reasonable. And therefore I'm going to plot 0.75. And when you move the load to the middle of the beam, the reaction over on the left-hand end went to 0.5. And when you move the load to the 3/4 point, the reaction on the left-hand end went to 0.25. And when you move the load to the end of the beam, the reaction on the left-hand end went to 0. That is an influence line. It's not a shear diagram. It's not a moment diagram. It tells you, when the boss comes and says, if I put the load right here, how much reaction at A will result. In other words, I need the influence of the 1 pound or 1 kip or 1 Newton force rolling across the structure. I need his influence on I, L, R sub A. Now, believe it or not, that tells you where to put the loads. For example, if I had a truck that's got a little wheel on the front that weighs 20 kips and a big wheel in the back that weighs 50 kips, phooey. If I got a truck that's got a 20 kip load in the front and a big wheel in the back which has got 50 kips on it, and they are 5 feet apart, the world's shortest truck, it tells you where to put the truck to get the biggest reaction at A. And that's something until now you probably really couldn't do. Number one, to get the biggest reaction at A, would you have the truck going east to west? You wouldn't, would you? You'd turn the truck around the way I had it the first time, so the 50 kip load could be placed where it causes the most reaction at A, and then the 20 kip load would just go over here 5 feet and add this much reaction at A. It tells you where to put the truck. It tells you which way to make the truck go. Here is an influence line for the reaction at B. When you put the unit load on the left end of the beam, it causes no reaction at B. When you put the load at the quarter point, it causes 0.25. When you put the load in the middle, it causes 0.5. When you put the load at the 3/4 mark, it caused 0.75. And when you put the load right on top of the reaction at B, it caused a full 1. And there is your influence line for the reaction at B. Skateboard. I thought maybe that was homework. Make sure I don't forget that stuff. Okay. Questions? All right, let me take the same beam and draw an influence line for the shear immediately to the right of the reaction. This is an influence line for the shear at what they call A plus. That means A is the pin slightly to the right of A. First, I have the load on the asphalt. Causes no shear in the beam. Then I put the load right on top of A. Causes no shear in the beam. Then I move the load very slightly to the right of point A, to the right of where the beam starts. It's a 1. This is 12 feet to the load, actually 12 minus, and it is 12 feet to the reaction, maybe even 12 plus. And I draw you a free body of the beam. There the beam is cut. Now, let me think about this. Let me draw the other end. It doesn't make any difference which end I draw, but I want to keep on using this same end. There's the beam. I don't even see how you see it. It's so short. Here's the reaction. When you put the 1 kip load on the beam, how much reaction do you cause? 1 kip, correct. 1 kip. This is 1 kip. You'll notice that my slice line, I moved the load on the beam a little to the right, so you can't, I'll show you that lightly, but you can't see it. And there is a shear that you caused inside of the beam of 1 kip. The reason is that little piece of steel has to be in equilibrium. Now then, if you did do the other end, here's what you'd see. You'd see the beam. You'd see the reaction at B. You'd see he has a 12-foot moment arm. You'd see this guy has a 12-foot moment arm. You'd see the shear going up instead of down. And 1 times 12 is balanced by somebody times 12, and therefore there'd be a 1 kip there. So you can draw either side, and you still get the same result. Now then I'm going to move the load to the, you know what? These influence lines, they look like they come out straight lines. So I'm just going to go get 3 points to make sure I don't have a curve on my hand. And I don't know what I'm going to get out of this case right here. But if I get like a point here and a point at the quarter point and a point at the half point, if they come out straight line, I'm out of here. Here is the unit load on the real structure. It is going to cause a shear in the beam. Going back to the real structure, we already solved for this incidentally. When that was 3 feet and 9 feet, that caused a reaction. Check it out. 0.75 on the left, 0.25 on the right. So that's kind of nice. I don't have to redo that. And I am going to cut the beam very close to the reaction because that's where you've been asked for the influence. You've been asked for the influence inside the beam in shear, slightly to the right of point A. Here's the free body. Here's the 0.75 reaction. Here's where you cut it. And here is the resulting shear inside the beam. I have 2 points on the influence line. Number 1, when the load is pretty close to the left end, but still to the right of the cut face, how does it influence the shear at that point? Number 2, when the load moves to the 3-foot mark, how much influence does it have on the shear slightly to the right of A? Number 3, when you put the load in the middle, when you put the load in the middle, I know I'm going to get a half a kip here and a half a kip here. And I want to know the influence on the shear slightly to the right of that point. Here's your free body. The length of that little piece right there is 0. Here's the 0.5 reaction on the left end. Here is the shear caused by the 1 kip load at this position, 0.5. Now, the real critical thing that I hope you see, and it may be so obvious you don't see why I don't understand, you see it, is that you don't plot the answers at this point. If you would, please all turn on your cell phones. That's the only way some of us are going to stay awake. Right, Galvin? I may get you to go sit next to him. That way it'll keep him awake. You plot the answer for the shear at this point where you put the load. That's its influence. And therefore, here is the influence line for the shear at A+, slightly to the right of A. The first value is 1. At the quarter point, well, I'll be darned, look at this. At the quarter point, it's 3/4. At the half point, it's a half. You know, mighta, shoulda seen that. Because the reaction at A, whatever the reaction at A is, that's what's causing the shear just to the right at A. And therefore, it's going to look exactly like the influence line for the reaction at A. There's your influence line for the shear at A. Again, if you got a truck with a big wheel and a little wheel, you should turn that truck around, should put the big wheel where the big value is, and you ought to put the little wheel wherever it comes out. And the final answer for the shear at A is how big is this wheel times 1 plus how big is this wheel times however far it is out. The sum of those two numbers will give you the total shear at A. Not an easy thing to see, not an easy thing to do. Not easy to know where to put a dang big old truck so that it causes the biggest moment in the beam. You've always been told the truck is here. In the real world, the truck is somewhere. And if you don't have some methodical way to find out where to put the truck, you're going to have a lot of shear and moment diagrams until you get the biggest one. Here is the influence line for the shear at the 6-foot mark. Same beam. Here's the beam. Here's the reaction. Here's the reaction. First off, we put the unit load just barely on the span, and we cut the beam at the 6-foot mark, and you take either side you want for a free body. It's your choice. Incidentally, I now know these reactions. I'm just going to go pull them off a previous page. When you put a 1 kip load just barely on the beam, it causes a 1 kip reaction and a 0 kip reaction. Here is your free body. Interesting. How much shear is caused at the 6-foot mark when the beam is loaded with the 1 kip load just barely on the span? 0 is correct. There's somebody who wants to go home sometime today. The shear is equal to 0. Don't forget that number. I intend to plot it at this location. I'm not going to plot it where I found the answer. I want to know this guy's influence on the shear at the middle. And so I'll plot his influence at the point where the load was when we worked this problem. Next, I'm going to put the load at the quarter point. I already know the reactions. Go back on a previous page and look. This number is 0.75. This number is 0.25. The beam is again cut at the 6-foot mark. Here's what the free body looks like. reaction on the left end is 0.75, and the load at the 3-foot mark is 1. There's my shear. Incidentally, I'm going to use positive shears. I'm just going to stick them on there positive. If they come out minus, I'll plot them below the line. Which way will I plot them if they come out minus, Morrison? You're not sure? Well, ask whoever you're texting there. No, how you're texting. Yeah, I know. You say, which way does the shear go? And you say, gee, honey, I don't know. What's a shear? And the answer is, Emeraj? Well, sure you do. I mean, anybody knows how big that shear is given these loads on the beam. I mean, you weren't texting, right? Well, see, you know, she knows. Sadly, you know, she was broken from her reverie from 0.25. It's the out of balance. And not only that, it's shown wrong. This guy's already beaten up on this guy. This guy needs help. This arrow is really the wrong way. But I'm leaving it shown positive, and I'll list it with a minus, 0.25. Means that when I see the minus sign, it helps me remember to show it plotted below the line. Here is the answer, or here's the case, where I'm going to put the 1 kip load at 6 foot minus, just very barely to the left of the point where you have been asked to solve for the shear. Pick somebody at random. Morrison, what are the reactions? Now, if you have a symmetrically loaded beam and you can't tell me the reactions, I'm gonna throw something at you. And it won't be small either. All right. And therefore, we draw a free body of our beam. And it has 0.5 on that end. Because the load is slightly to the left of where we're looking for the shear, you will still see the 1. You'll see the cut face. You will see a shear like this. If it's wrongly drawn, I'll get a minus sign, and I'll be plotting that number below the axis. Kruger, what is the answer for the shear? Kruger here today? We need a pop quiz. That's what we need. Bourne, minus 0.5 is correct. Now then, I'm going to show you the unit load placed just barely to the right of the cut face. Come on, it's not that bad. It must be the way he looks. 6 feet plus. Did you already have this class?
No.
No? Well, this ought to be new.
I'm just full-time.
Okay. You're sure noisy. The reactions don't change because you didn't move the load. You say, oh, I did move the load. No, you didn't. You think you did, but you didn't move it enough to change anything. And here is your free body. And here is a free body just of the cut that you have. This is still 0.5. Here's the shear. Believe me, they're always going to be shown down on the right. That's what a positive shear is. Ooh, look at what happened. All of a sudden, the 1 kip load moved to the right of the cut face, and the shear changed from a minus 0.5 to a plus 0.5. Question? We okay? All right. Finally, I'm going to draw the beam. I'm going to show the 1 kip load. You know, I only told you I was going to do a couple of points because they were always straight lines. And it turns out they really are. They're always straight lines. The only thing is the shear diagram, oh, whew, that's bad. The shear influence line's got a kink in it, but it's still made up of a pair of straight lines. When this is 9 feet to the right, the reactions, let me check, here they are, 0.25 and 0.5 to 75. There, yeah. Then here's your free body cut at the 6-foot mark. And so here's your free body. And there's the shear. And here's your reaction, 0.25. And the answer for the shear is 0.25 kips. Now then, I have moved the load across the beam, and I know how it influences the shear at the cut, at the point of interest. When the unit load is here, causes no shear. When it's moved, causes minus 0.25. When it's moved to the 6-foot mark, minus 0.5. When it's moved across the cut point, the point we're looking for the influence line, changed signs, and when it went out to the 9-foot mark, it got to be 0.25, and I guess I can draw that last one. When the load is moved to the 12-foot mark, this shear will be 0. Now I'm ready to plot it. Here's the beam. When the load is on the left end, the shear is 0. When the load is moved to the 3-foot mark, the answer is minus 0.25. Half, quarter, quarter, end. Minus 0.25. When the load is moved to the 6 minus mark, the answer is minus 0.5. See, I told you those are straight lines. When the load is moved slightly to the right of the point we're looking for the influence line, it turned to a plus 0.5. When it moved to the 9-foot mark, it got to be 0.25. And when it went to the end, it got to be 0. There's your influence line for shear at the middle. Who needs to know the influence line for the shear at the middle? Well, you do, because the boss is going to come by and say, Joe, go tell me what steel section, how many steel plates I need to resist the shear at the left end. And he'll be drawing this influence line right here, and he'll know where to put the wheels and which direction to go, and he'll be able to calculate the biggest shear possible from that truck, and he'll be able to design the beam. In the middle of the beam, you'll notice the influence is less really a minus. We don't usually put the minus because it's shown below the line. And you'll know where to put the truck. You'll put the big wheel here, and you'll put the little wheel here, or you'll put the big wheel here and you'll put the little wheel there, and you'll multiply the magnitude of the little wheel, big wheel, times 0.5, and I don't know where this one is, but you'll multiply its value times that influence. You'll add them together and you'll be able to design the beam for shear at the middle. And it'll do every point along the beam to make sure that the shear doesn't get too big. Now, if you say, this is horrible, is this what structural engineers really do? That could take a day. As a student, you say, that could take a day. As an engineer, you say, that'll take a day. It's true. I've done it. I mean, you know, I really try and get through as soon as I can because that's the ethical thing to do. But when I know it's going to take another day, I don't say it's going to take another day. I don't even think about that. All right. Now then, I would like to know the influence. Yes, sir.
So, can you explain again why you chose to cut it at 6 feet?
I really can't because there was no reason at all. Because in the real world, you'll generate an influence line for the shear at the left end, the shear at the quarter point, the shear at the middle. If it's symmetric, you'll go ahead and you won't do the quarter at the 3/4 point. And because you're really looking for the maximum shear that's going to be in the beam in a certain region. So the point that you will pick in this class, you'll be told, give me the influence line in the middle for shear. In the real world, you'll get several of them. All right. Let's see who's here today. This is the influence line for shear at the 15-foot mark. I don't expect that you know where it came from at all, but I'm just telling you that is the influence line for a simply supported beam for shear at the 15-foot mark. The whole beam is 20 feet long. I have a truck, and it's got a big wheel on it. It's called a uni-wheel truck. And it is a 30-kip wheel. The influence line is 0.75 and a 0.25. Boy, they are really desperate. And I want you to tell me how much shear is caused at the 15-foot mark when you see the influence line as shown with a single 30-kip wheel. And I want the max negative. So whoever was ready to hand their problem in, you're probably going to have to change it now. Who's through? What'd you get for an answer, Megali?
You're saying to put the wheel where you're getting the maximum negative shear, right?
That is correct. I agree, 7.5. Well, no, I think you probably ought to write down negative 7.5. And I also, if you're not going to hand in that sheet, no problem, not necessary. If you signed it and if you're going to let ABET see your stuff, just put it right with your pop quiz. Yes, sir.
I have a quick question. It's not related to topics in this class, but it's just something simple.
All right, hang on a second. Let me go ahead and turn this thing off.